Assalamu alaikum and hello. My name is Rahman Kazi Faridur. Today I am going to give a presentation of INE 504 project. The project topic of mine was photodiodes. Three scientific journals have taken here. Now let's get started. Okay, here we can see the three journal list. The first journal list is analysis on different detection mechanisms involved in zinc oxide based photodetector and photodiodes. The second one is fabrication and characterization of solution processed aluminum zinc oxide PSI photodiodes. And the third one is weighing detection with near-infrared organic photodetectors for biometric authentication. Now, the first journal is analysis on different detection mechanism involved in a zinc oxide-based photodetector and photodiodes. The executive summary of the paper. In this paper, a comparison between the ultraviolet light detection mechanism in zinc oxide based photodetectors and zinc oxide PDOT to PSS hybrid photodiodes has been made. Using spray pyrolysis method, zinc oxide thin films were deposited upon glass substrates. The deposition temperature was varied from 350 to 425 degrees Celsius, and the physical properties of the zinc oxide thin films were investigated. The structural analysis reveals that all the prepared zinc oxide thin films have a preferred orientation along the 002 plane with hexagonal Arterized structure. The morphological analysis reveals that the grains are uniformly distributed. Electrical properties reveal that the zinc oxide thin film deposited at 425 degrees Celsius shows a higher carrier concentration of 3.76 into 10 to the power 16 centimeter per cube with low electrical resistivity value of 2.59 into 10 to the power 2 ohm per centimeter. For fabrication of UV photodetectors, the optimum zinc oxide layer with good electrical and optical property was deposited on indium tin oxide or ITO substrate with substrate temperature maintained at 425 degrees Celsius. For the fabrication of hybrid ultraviolet photodiodes, poly 3,4-ethylene dioxythiophene is to polystyrene sulfonate PDOT-PSS and zinc oxide was used as the hole and the electron transporting layers respectively. Now the research methodology. I have divided the research methodology into two parts. The part 1 is preparation and characterization of the thin film. Here we can see that the zinc thin films deposited by spray pyrolysis. After that, the preparation of the precursor solution is started. Then the zinc oxide thin film samples deposited at 350 degrees Celsius, 375 degrees Celsius and 400 degree and 425 degrees Celsius. After deposition, then using the spin coating method, the PDOT to PSS layers were deposited on a clean glass substrate. The PDOT to PSS thin film samples coated at 1000 rpm, 1500 rpm, 2000 rpm and 2500 rpm. After that, the structural investigation was studied using X-ray diffractionometer. Then the thickness of zinc oxide and PDOT to PSS thin films were measured using stylisis profilometer. The morphological analysis of zinc thin films was studied using ZSIS Ultra 55 with Oxford EADX system. After that, the transmission and absorption spectra of the prepared zinc oxide thin film were studied using JESCO V670 UV VIS NIR spectrometer. Then, Hall measurement system was used to study the electrical properties. After that, JESCO spectrofluorometer FP8500 was used to study photoluminescence spectra of the deposited zinc oxide thin films. Now the part 2, which is fabrication process. Here we can see that the indium tin oxide thin film layers were deposited by RF sputtering on the clean glass substrate. After that, using the spray pyrolysis method, the optimum zinc oxide layer with high transparency and lower resistivity were deposited on ITO coated glass substrate. After that, the PDOT is to PSS layers with low electrical resistivity and high hole concentration were deposited upon the zinc oxide layer using spin coating method. Then we can see that the silver was deposited as top electrodes using the thermal evaporation techniques. Now, the result and the discussions of this journal. From the result and the discussion, there are several subsections. The first one is the structural studies. From this journal, the structural studies are as from the figure 1. This is the figure 1. We can see that the X-ray diffraction XRD pattern of zinc oxide 350, zinc oxide 375, zinc oxide 400, and zinc oxide 425 thin films. Here, all the thin films have been seen in the figure 1. The intensity of OO2 diffraction peak is higher. We can say that the intensity of OO2 is higher, which was every intensity of OO2 is higher. The surface free energy of OO2 plane is lower than of other planes. The deposited samples are pure and free from impurities because zinc oxide films do not show secondary phases. We can see from the figure there, the zinc free oxide films do not show any secondary phases because the deposited samples are very pure. The intensity along OO2 peak increases with the increase of deposition temperature. We can see here from here that while the temperature increase, the intensity also increase. At higher substrate temperature, the FWHM of OO2 peak decrease. The crystalline size of the zinc oxide thin films were calculated by using scalar formula. From the table 1, we can see that table 1 shows the lattice constant, the C value, this one the lattice constant, stress, strain, and the crystallization size of zinc oxide 350, zinc oxide 375, zinc oxide 400, and zinc oxide 425 thin film samples. Here we can see that the lattice constant C value decreases with the increase of the deposition temperature. The temperature will increase, the lattice the lattice constant value C decreases. Like the first one is 5.172, then it decreased to 5.161, then 5.155, and then the 5.153. The increase of the deposition temperature, the decrease of the constant value C. The positive zinc oxide thin film state tensile stress, this is the stress uh, which is positive, so these are the tensile stress. The negative Z-ono film state comprehensive stress. The negative Z-ono films is known as compressive strain. The strain in the zinc oxide film was inherent rather than thermal. Now, the next one is morphological analysis. From the figure 2 illustrated, the FESEM morphographs of a zinc oxide 350 and zinc oxide 425 thin films. It was observed that the grain size increases with the increase of substrate temperature. The analysis also reveals that the formed grains were dense and uniformly distributed with the varying size. We can see from this figure 2. Now is electrical studies. Electrical studies, from the table 2, we can see that the table 2 represents the electrical analysis of zinc oxide 350, zinc oxide 375, zinc oxide 400, and zinc oxide 425 thin films. The observed electrical resistivity value decreases from 5.06 into 10 to the power 2 to 2.59 into 10 to the power 2 ohm centimeter. Zinc oxide 425 shows the higher electron concentration. From the table we have seen these things. Grain size is important because the larger grain size contributes to enhancement in the carrier mobility and reduces the scattering of the electron from the grain boundaries. Table 3 illustrates the electrical characteristics of P dot 1000, P dot 1500, P dot 2000 and P dot 2500 thin films. Now the optical studies. From the figure 3, it demonstrates the optical transmission spectra of a zinc oxide 350, zinc oxide 375, zinc oxide 400 and zinc oxide 425 thin films and P dot 1000, 1500, 2000 and 2500 layers. The average transmittance value in the visible region for zinc oxide and P dot PSS thin films are 60% and 85% respectively. The optical transmittance of zinc oxide thin films deposited at lower substrate temperature decrease due to the incomplete decomposition of precursors which create defects in the lattice and absorbs more visible light. The band gap of zinc oxide thin films was calculated by extrapolating the linear part of Stokes plot alpha hv into 2 versus photon energy as shown in the figure 3c. From the figure 3c we can see this thing. The band gap of for zinc oxide thin films, the band gap values decreases from 3.27 to 3.21 electron volt with the increase of the deposition temperature. With the increase of the thermal energy substrate temperature, the amplitude of atomic vibrations increases and lowers the potential of the semiconductor electrons. It reduces the band gap values. Here, the band gap values of the zinc oxide thin films decreases from 3.27 to 3.21 electron volt with an increase of deposition temperature. Now, photoluminescence studies. Figure 4 illustrates the photoluminescence PL spectra for zinc oxide 350, 375, 400 and 425 thin films. It was observed that all zinc oxide thin films shows four distinctive peaks at 380, which is 3.26 into 10 to the electric volt. At 470, the electric volt is 2.63, in 490, 2.52 electric volt, and in the 522 nanometer, which is 2.37 electron volt. The emission peak at 380 is ascribed to the near band emissions. The broad spectrum in the visible region was analyzed using Gaussian fitting to study the blue 470 nanometer and 492 nanometer and green 522 nanometer emission. For zinc oxide thin films, the significant contributions towards PL emissions are primarily due to the zinc interstitial site and oxygen vacancy defects. Due to the recombination of zinc interstitial energy level and zinc vacancy, the blue emission at 470 and 492 nanometer were obtained. The green emission peak at 522 nanometer is due to oxygen vacancies which are formed at the deep donor level in the band gap of the material. The intensity in the visible region decreases with the increase in the substrate temperature. Now the Raman spectra. Figure 5, this figure 5 shows the Raman spectra for P dot to PSS, P dot 1000, 2000 layers respectively. The P dot vibration modes obtained at 1536 centimeter, 1, 1407 centimeter, 1363 centimeter, and 1248 centimeter were assigned to the asymmetrical C alpha in equal to C beta, symmetrical C alpha equal to C beta, stretching C beta, and interring stretching C alpha dash vibrations respectively. The PSS vibrations modes were observed at 1094 centimeter and 990 centimeter. The vibration modes obtained for P dot and PSS were in good agreement with the earlier reports. For the fabrication of zinc oxide based photodetectors and hybrid photodiodes, the optimum zinc oxide and P dot PSS layers were used. The following device configuration at ITO in zinc oxide silver photodetector and ITO zinc oxide PSS silver hybrid photodetect diodes. Figure 6 here, the figure 6 illustrates the schematic device structure of an indium tin oxide and zinc oxide silver photodetector or in and indium tin oxide zinc oxide PSS silver hybrid photodiodes. This one the ITO the B which was indium tin oxide zinc indium tin oxide zinc oxide period PSS and silver, and this one is the first one, it's indium tin oxide zinc oxide silver photodetector. Now current voltage IV characteristics from figure 7a. This from figure 7a illustrate the current voltage characteristics of zinc oxide based photodetector measured under dark and ultraviolet illumination. At 3-volt reverse bias, the current value of zinc oxide based thin film photodetector under dark and ultraviolet illumination were measured as 4.4 milliampere and 5 milliampere respectively. The graph illustrates linear behavior which indicates that zinc oxide and silver electrodes show ohmic characteristics. From the figure 7b shows the current voltage characteristic of zinc oxide based hybrid photodiodes measured under dark and ultraviolet illumination. The observed rectifying behavior was attributed to the formation of the barrier at the interface between P dot to PSS and zinc oxide owing to the energy level difference. At 3-volt reverse bias, the current value for zinc oxide based photodiode was measured at 0.012 milliampere and 1.02 milliampere for dark and ultraviolet illumination respectively. Now, photo response switching characteristics. Figure 8 shows the photo response switching characteristic of indium tin oxide and zinc oxide silver photodetectors and indium tin oxide zinc oxide P dot PSS silver hybrid photodiodes. When zinc oxide based photodetector was exposed to the incident ultraviolet light source, the photocurrent increased sharply, and upon termination of light and the photocurrent drops gradually to its initial stage. The stability of the fabricated devices were confirmed by various on-off cycles. The rise and recovery time of the zinc oxide-based photodetector was measured as 2 seconds and 65 seconds respectively. The quick rise time is due to the formation of more number of photo-generated electron and hole pairs, which increases the electrical conductivity. The rise and fall time of the zinc oxide P dot PSS silver photodiode was measured as 0.7 and 2.95 seconds respectively. The photoresponsivity of N zinc oxide silver photodetector and ITO zinc oxide P dot PSS silver photodiodes were calculated as 0.14 and 0.25. The external quantum efficiency of the zinc oxide silver photodetector and indium tin oxide zinc oxide P dot PSS silver photodiodes were calculated at as 47.56% and 81.53% respectively. The detectivity D of the fabricated photodetector and photodiodes were calculated as 0.37 into 10 to the power 10 and 1.27 into 10 to the power 11 joules. The detection mechanism. The detection mechanism is divided into two parts. One is zinc oxide based photodetector. The figure 9, the whole figure 9 shows the schematic diagram illustrating the oxygen absorption and desorption process on the surface of the zinc thin films under dark and ultraviolet illumination. The mechanism can be understood by following steps. During the dark condition, the oxygen molecules from the air atmosphere get absorbed upon the surface of the zinc layer. The absorbed oxygen has the tendency to react with free electrons from the conduction band of zinc oxide and forms negatively charged oxygen molecules. When zinc oxide thin films are illuminated by ultraviolet light with the condition EHV is greater than EZNO, the electron hole pairs were generated. The photo-generated carriers reach the zinc oxide surface and neutralize the absorption oxygen by the process termed as photodesorption. Here you can see the photodesorption. Now the second one is zinc oxide P dot PSS, zinc oxide P dot PSS photodiodes. Figure 10 represents the schematic energy level diagrams for a silver zinc oxide photodetectors and P dot PSS zinc oxide hybrid U ultraviolet photodiode. In the case of zinc oxide based photodetectors, a junction is formed between the silver and n-type zinc oxide layers. We can see uh, um, from the figure that a junction has been formed between the silver and zinc oxide layers. Okay, as the depletion region extends to certain depth in the semiconductor, energy band level bends from the n zinc oxide to the silver electrode as shown in figure 10a. We can see from the figure 10a we can see it from the figure 10a that when the depletion region extends to certain depth of the semiconductor, energy band level bends from zinc oxide to the silver electrode. So zinc oxide to this silver electrode, like this band. You can see. In the case of zinc oxide based photodiodes, when the PDOT, PSS and zinc oxide layers are stacked together, the charge carrier migration takes place between the PDOT, PSS layers and the zinc oxide thin film until an equilibrium state is attained. As a result, the depletion region is formed at the zinc oxide PDOT, PSS interface and a potential difference has been informed as the junction is shown in figure 10b. Here we can see the everything. The zinc oxide here, there is a valence band and it is the conduction band. Okay. Now we are going to start the journal 2, which is called the fabrication and characterization of solution process aluminum zinc oxide p silicon photodiodes. The executive summary of this journal is: this study describes the deposition of zinc oxide thin films with various session dropping concentration by a solution-based spin coating method. The effect of the acid doping structural zinc oxide thin films and optoelectrical features of zinc oxide based photodiodes have been investigated. As a result of the structural analysis by XRD and AFM, the thin film shows an amorphous nature and the surface roughness decreasing with the sand dropping. The electrical analysis is revealed that the fabricated diodes showed a high reflection ratio, which is known as R, the reflection ratio. The maximum reflection ratio value of 4.38 into 10 to the power 4 at plus 4 volt and minimum reverse bias current were obtained from SZO10 10% tin doped zinc oxide. Also, All diodes indicated good photodiode characteristic and highest responsivity value of 1.68 was obtained from SHZ-010 as the result of photosensitivity. The obtained result shows that the tin doping improved the electrical, photoelectrical and optoelectrical characteristics of the zinc oxide based photodiode. Okay, now we have reached on the slide which is called research methodology. Here I have divided the research methodology into two parts. The part one is the fabrication of photodiodes. At first, the amorphous zinc oxide thin films were deposited as the function of tin doping on P silicon by Solzhenitsyn spin coating method. Then 0.05 m zinc acetate dihydrate and 0.05 m tin chloride were dissolved into methoxide ethanol respectively. After that, the monoethanolamine MEA was used as a stabilizer for both precursor solutions. Undoped and tin doped solutions were stirred at 60 degrees Celsius for 2 hours. After that, doped and undoped and tin doped films were deposited on P-silicon at spin speed of 3000 rpm for 30 seconds in the room temperature and then dried at 300 degrees Celsius for 10 minutes in an oven. After that, the deposited films were annealed at 750 degrees Celsius at a furnace for 2 hours. After that, aluminium ohmic electrodes were evaporated on top of the thin films through the shadow mask. Then the silver paste was coated on the backside of the P silicon to complete the fabrication of photodiodes. The part 2 is called the characterization. Here, the Broca D2 phasor X-ray diffractiometer XRD and anti-MDT nano educator to model atomic force microscopy AFM were used to determine the crystalline structure and surface roughness of the obtained films. Then all electrical analysis of diodes was performed by Catheli 4200 SCS system. To investigate the photoelectrical characteristic of diodes, all the diodes were illuminated by the AM 1.5 light from a solar simulator equipped with a 300-watt XE lamp. Now the result and discussion. From the measured survey spectrum illustrated in figure 2a, the figure 2a is this one, which confirms the existence of zinc, oxygen, carbon and tin elements. The atomic percentage of tin element were determined to be at 0.652, 2.681, 4.843 for SZO1, SZO5 and SZO10 respectively. The figure 2b shows the doubled paired peaks of the zinc 2p core levels separated from each other by 23.0, 23.09 electron, 23.09 electron volt. These doubled peaks are observed about 1021 electron volt and 1044 electron volt for binding energies of zinc 2p 3 by 2 and zinc 2p 1 by 2 respectively. In figure 2c illustrates the oxidation stage of tin for all films. In this figure, tin 3D 5 by 2 and 3D 3 by 2 core levels having the binding energies at around 486.5 electron volt and 495 electron volt are seen as separated by 8.5 electron volt from each other, and also these binding energy values indicate that tin has 4 p oxidation state in our samples, and also doubled pair peaks of the tin 3D are becoming more pronounced as increasing SN doping ratio. O1 second spectra have been investigated for all films and obtained results are illustrated in figure from 3a, b, c, d. In this figure, it is seen that the Gaussian Lorentzian curve fitting have two peaks around 530 electron volt and 531.7 electron volt. The low binding energy value is related to the oxygen ions in the zinc oxide lattice, and the higher one is related to the oxygen vacancies. As seen in these figures, oxygen vacancies values slightly decrease as increasing tin doping ratio. Atomic force microscopy, or AFM, was used to investigate the influence of tin doping on the zinc oxide thin film surface morphologies. The atomic AFM images of deposited thin films are illustrated in Figure 4. It is clearly seen from Figure 4 that tin doping strongly affects the surface morphologies of zinc oxide-based thin films. That is, while the surface morphology improves due to the increasing doping ratio, a decrease in the grain size is also observed. The root mean squares RMS roughness value of thin films, which is one of the key parameters of surface characterization, decreases regularly when the tin doping increases. The RMS value of zinc oxide SSO1, SZ05, and SZ010 are 37.99 mm, 26.14 mm, 13.47 nanometer, and 7.23 nanometer respectively. Zinc oxide thin films illustrated a decreasing trend with the tin doping. This decrease can be ascribed that the difference ionic radii between SN4P and zinc 2P. Furthermore, the decrease in surface roughness can be explained by the decrease in grain sizes of thin films. Using thin film with a smooth surface has an advantage because of suppressing interface traps and scattering centers. The XRT spectra of the zinc oxide and SSO films are illustrated in Figure 5. It is seen from the Figure 5 that all films have amorphous nature due to the absence of any sharp peak. The experimental semi-logarithmic 1,4 logarithmic IV characteristics of the fabricated photodiodes under dark and different light intensity at room temperature are shown in Figure 6a to d to obtain electrical parameters of diodes. It is obvious from these figures that all fabricated diodes indicate nonlinear IV and rectifying behavior with rectification ratio values between 101 to 104. Also, it is seen that the IV characteristics of the diodes are clearly influenced by the concentration of tin doping. As shown in Figure 6a to d, the forward bias current of the diode shows an increasing trend with the tin doping, and it has also caused an increase in the RR value of the diodes. Table 1 represents the calculated device parameters of the aluminum, tin, zinc oxide, PA silicon devices for variation of tin doping zinc oxide interface layer by using a standard diode equation nu, nu, which is known as the ideality factor, has been calculated. The calculated nu values of the fabricated heterojunction diodes are given in Table 1. The saturation current is extracted from the intercept of ln IV graph at 0 volt and expressed an equation. By using that equation, sigma B have been calculated and summarized in the Table 1. It has seen in from Table 1 that the sigma V values of diodes tend to increase with the increase of tin doping. This increase in sigma B can be attributed to the fact that the low Schottky barrier height regions at the interface are less and more electron will have enough energy to overcome sigma B while the dopant concentration increases. Figure 7 represents the energy band diagram and the charge transport of the fabricated photodiode under reverse bias. The energy band diagram of the diode in figure 7 is useful of, for examining the IV characteristics of the heterojunction diodes under light. Since zinc oxide has high transparency, the visible region of the incident light passes through the zinc oxide thin films and is absorbed by PSI, while the UV part of the incident light is absorbed by zinc oxide. When the high energy HV is greater than EG, photons absorbed by SZO films, the electron hole pairs are generated in the photodiode. Here you can see the photodiode energy generator hole is generating. The ratio of photocurrent to dark current defines the photosensitivity of diodes. I photo by I dark. The photosensitivities of of diodes were calculated at 100 milliwatt per centimeter square for white light and tabulated in table 2. It is seen from table 2 that photosensitivity of photodiode increases with increasing tin doping. The highest photosensitivity of 104 was obtained from SZO10 photodiode at 100 milliwatt per centimeter square under 4 volt. It is well known that the RS is an important parameter due to its current limiting role in heterojunction diodes and can be defined by various techniques such as Nord or Cheong methods. By means of these methods, the RS of the diodes as well as the sigma V and the new values can be calculated from the typical IV data. Figure 8 represent the node function voltage FV curves of the fabricated zinc oxide and SZO photodiodes. Figure 10a illustrates the responsivity of zinc oxide based photodiodes as a function tin doping for 100 milliwatt per centimeter square at 4 volt. The obtained or responsivity values of photodiode are given in table 2 that we have seen earlier. The highest responsivity value of 1.68 was obtained from SZO10 as the result of photosensitivity. This high value of responsivity can be attributed to a high built-in barrier potential of SZO. High built-in potential improve transportation process and charge separation and p-n heterojunction structure. The photoconduction mechanism of diodes can be analyzed by the following equation, which is IPH 1 by 4 AP del, where IPH, AP, and del are photocurrent, constant light intensity, and illumination coefficient respectively. The slope of the log IPH versus log P is used to find the value of del. Here is the log P by log I, log IPH by log P. From here we can find the value of del. Therefore, the plot of log IPH versus log P is shown in figure 10b. Here we can see the figure of log IPH versus log P. Figure 11a to D shows the CV curve of photodiodes with various tin doping to further investigate the electronic parameters of diodes in the frequency range of 10 kHz to 1 MHz. It is clearly seen from the CV curve the capacitance value diode is strongly influenced by both frequency and applied voltage. After a certain positive voltage in the forward region, the capacitance value of the diode decreases with increasing frequency due to the presence of interface states between zinc oxide and P silicon. The interface states of diodes cannot flow the AC signal at the higher applied frequencies. Therefore, the interface states cannot contribute to the capacitance of diode, and the capacity value of the diode is lower at higher frequency. Among all photodiode, SZ05 has only negative capacitance for 1 MHz at a high forward bias region. The conductance voltage GV graphs of diodes are shown in figure from 12A to D. The value of conductance almost remains constant under reverse bias region and increases under forward bias with increasing frequency. This case explains the existence of the interface states as in the CV.4. Now we have finished the journal 2. Now we will start journal 3, which is known as vein detection with near-infrared organic photodetector for biometric authentication. Now, the executive summary of the journal 3. In this paper, a low dark current and high detectivity near-infrared NIR sensitive organic photodetector with a high resolution 508 pixels per inch PPI oxide thin film transistor TFT backplane to create a large area thin NIR detector using processes that are compatible with flat panel display fabrication have been combined. The detector is characterized showing high uniformity and linearity. With the use of a NIR light source, the detector is capable of imaging the pattern of veins under the skin in reflection, leading to improved biometric authentication. The research methodology here, it is the fabrication of NIR organic photodiodes. Here at first, indium tin oxide coated glass substrate is used as a transparent conducting anode. After that, active size of organic photodiode is defined by patterning of IPO coated glass substrate using photolithograph technology. Then, active layer of organic photodiode is deposited onto this patterned IPO coated substrate through shadow mask in E-beam evaporation thin film deposition unit under a pressure of 10.5 to 10.6 mbar. After the cathode Al by Au would be evaporated onto the organic layers through shadow mask in the same EB evaporation unit under a pressure of 10.5-10.6 bar. Then, to obtain a clear image of vein pattern, NIR light is added. Now the result and discussion. The result and discussions is at first 3.1, it is NIR organic photodetectors. Here, the OPD, which organic photodiodes, consist of a blend of the polymer poly 2,5 bias 2 hexyldecyl 2,3,5,6 tetrahydro 3,6 dioxopyrrole 3,4 C pyrrole 1,4 1,4 di ALT 220 50 200 tetrophene 500 diene PDPP 3T with the fluorine phenyl C61 butyric acid methyl ester PC61BM, which is shown in figure 1a. This one is the equation. The effective band gap Eg of this BHJ OPD blend is 1.03 electron volt. The OPD blend was mixed in a 1:2 ratio dissolved in chloroform with 7.5% of ortho-dichlorobenzene. Editor promote the phase separation of both components of active layer. The active layer was stirred at 90 degrees Celsius overnight and then processed from solution by spin coating, resulting in layers of 280 nanometer. The full device architecture can be seen in figure 1b. Amochromium 130 nanometer reflective and ITO were both sputtered and used as bottom and top electrodes respectively, whereas molybdenum oxide MOOX evaporated and IGZO were used as hole and electron extraction layers respectively. Devices were illuminated from the top through the transparent ITO contact, which is also required for the targeted application. The the two main figures of merit of optical photodiodes are current under dark conditions and the EQE, current density versus voltage, J versus V. Characteristics under dark were measured and are shown in figure 2a. The devices show an excellent diode behavior with a current a rectification ratio of 5 into 10 to the power 5. The dark current density ZD at 3 volt. Common operational voltage is 2.3 into 10 to the power minus 6 milliampere per centimeter square. The external quantum efficiency or the EQE was measured under a constant voltage of minus 3 volt. Uh, the devices show an external quantum efficiency of 40% at 850 nanometer and 7% at 940 nanometer, which is shown in figure B. These two wavelengths are purposely reported as they match with the wavelengths of most commonly available NIL light emitting diode LED light sources and are inside the optical window of vein detection applications. Additionally, the external quantum efficiency ranges between approximately 26% and 48% in the full visible spectrum 400 to 700 nanometer. The obtained external quantum efficiency values are high at 850 nanometer but decrease rapidly towards 1000 nanometer. Limited by the absorption of the BHJ blend, SR is the spectral responsivity derived from the EQE, and QE is elementary charge 1.6 into 10 to the power minus 19 coulomb. At 3 volt and 850 and 940 nanometer, the maximum detectivities are 1 into 10 to the power 13 and 1.8 into 10 to the power 12 joules respectively. 1 joules is equal to 1 centimeter hertz, half watt. Figure 2c. From figure 2, so you can find this one. Now 3.2, which is large area vein detection imager. A schematic of full detector is shown in figure 3a. The NIR OPT as described was used as the front plane building block for the vein detection image prototype. Figure 3b shows the circuit diagram of the device. A common anode configuration is used where the self-capacitance of the photodiode stores the charge. The back plane and the front plane stacks are topped by a conventional thin film barrier film that prevents all device degradation by moisture and ambient atmosphere. Figure 3c. All manufacturing processes are compatible with flat panel display fabrication, opening the possibilities for mass manufacturing. The optical and electrical properties of the vein detection image array were also characterized. First, current density was measured as a function of light power using 850 to 850 and 940 nanometer light sources. Flux ladder BL 100 into 100 L LUBQ1RC1 as shown in figure 4a. Blue and for a blue this one blue and red curves are for 850, this one is 850 and 940 nanometer respectively. The imager shows a linear response considering R2 equal to 998 up to light powers of 0.67 and 1.95 mu watt per centimeter square for 850 and 940 nanometer light sources. This corresponds to a light power per pixel of 7.1 into 10 to the power minus 12 and 1.8 into 10 to the power minus 11 watt. The linear dynamic range is 55 dB for LDR equal to 20 log Imax by Imean, where Imean is calculated from the measured noise current. The modulation transfer function MTF of the imager was measured, giving a quantitative indication of the spatial resolution of the system. For this purpose, the aforementioned 850 nanometer tile was placed at a distance of 1 meter to ensure normal light, and the slanted edge method was applied to obtain the MTF 18. The results are shown in figure 4b. Here we can see the results. The orange curve plotted together with the theoretical value black curve. Finally, in order to determine the uniformity of the pixel response, the current density of all pixels in the array was measured in dark and under light conditions 850 and 940 nanometer, both at light powers of 0.60 mu watt per centimeter square, and plotted in an histogram graph figure 4c. The vein patterns of a person can be used as identification data owing to the intersect and unique vascular patterns. Our imager was used to obtain the vein patterns of live subjects on different parts of the body. Images of veins of a hand, palm, and wrist are shown in figure 5. The system worked as follows. The target is placed above the imager in non-contact mode. Light is emitted from the NIR LED corona array towards the target. NIR light traverses human tissue and is absorbed by the hemoglobin in the blood in the vein vessels. Now, the overall comparison of these three papers. The first journal was analysis on different detection mechanisms involved in zinc oxide based photodetector and photodiodes. Here, using spray pyrolysis method, zinc oxide thin films were deposited upon glass substrate. The spray pyrolysis method was homemade. In this novelty, I think, in this paper, both zinc oxide-based ultraviolet photodetector and hybrid ultraviolet photodiodes were fabricated. Here, indium tin oxide thin films were used by RF sputtering on the clean glass substrate. The P.PSS layers with low electrical resistivity and high hole concentration were deposited upon the zinc oxide layer using spin coating method. Silver was deposited at top electrodes using thermal evaporation techniques. The second journal was fabrication and characterization of solution process aluminum tin zinc oxide p silicon photodiodes. Here, zinc oxide thin films were deposited by tin doping concentration by a sol gel coating method. Here, aluminum ohmic electrodes were evaporated on top of thin films through shadow mask. The silver paste was coated on the backside of p silicon to complete the fabrication of the photodiodes. The third journal was vein detection with near-infrared organic photodetectors for biometric authentication. Here they combine a low dark current and high detectivity near-infrared sensitive organic photodetector with a high resolution 508 pixels per inch oxide thin films transistor backplane to create a large area thin NI detector. The organic photodetector was fabricated here. Here, indium tinoxide coated glass substrate was used by using photolithograph technology. Well, the first and the third paper has used indium tinoxide thin films, but using different methods. The second journal is used ZNO thin films. The first two journal was based on zinc oxide based zinc oxide based photodetectors. The third paper was based on organic photodetectors. In the journal 3, a near infrared light was used to obtain a clear image of wind pattern, while the other two papers were just two comparisons between the same photodetectors using different methods. So from the above, these are the comparisons that I have found among these three papers. Now the overall conclusion. The conclusion of the journal was is in summary, zinc oxide photovoltaic thin films showed good structural, optical and electrical properties with electrical resistivity and electron concentration value measured as 2.59 into 10 to the power 2 ohm centimeter and 3.76 into 10 to the power 16 centimeter per cube respectively. The organic PDO layer showed low electrical resistivity value of 3.25 into 10 to the power minus 2 ohm centimeter. Using the optimum zinc oxide and the PDOT layers, zinc oxide based ultraviolet photodetector and zinc oxide PDOT PSS hybrid photodiodes were fabricated and the properties were investigated. The different mechanisms underlying between photodetector and photodiode device configuration were investigated. From journal to the conclusion is, in summary, undoped and tin doped thin film have been successfully deposited on P silicon with low-cost sol-gel spin coating method and their photodiode application were investigated. Electrical parameters of diodes were determined such as ideality factor, barrier height and series resistance. The fabricated diode showed in high RR value and the maximum RR value of 4.38 into 10 to the power 4 at 4 volt and minimum reverse bias current was obtained from SZO10. The highest responsivity value of 1.68 A watt was obtained from SZO10 as the result of photosensitivity. The conclusion of Journal 3 is, in summary, NIR of organic photodetector devices have been fabricated and optimized state-of-the-art that excel in all relevant photodetector figures of merit. Here, this organic photodetector used as frontline together with an IGZO backplane and an NIR light source to image vein pattern. So the summary is that after analyzing all three papers, the journal 2, which was fabrication and characterization of solution process aluminum tin zinc oxide P silicon photodiodes, is the best according to me. It is because here they have used sol-gel spin coating method, which is low cost. All diode indicated good photodiode characteristics. The highest resistivity value of 1.68 A watt was obtained from SZO10 as the result of photosensitivity. It is clearly seen from the results that the tin doping improved the electrical and optoelectrical characteristics of the zinc oxide based diode. Also, the obtained results from transient current and IV measurement under illumination indicate that fabricated heterojunction can be used as a photosensor. That's all. Thank you very much for listening my presentation. Assalamu alaikum warahmatullahi wabarakatuh.